as an example, let's take a look at example 14.1 in the textbook. This is page 352 of the textbook. I'd like to scroll down here. Oh, wait, next. Here we go. So example 14.1 says body mass index of young women. So it says an NHANES report, whatever kind of report that is, gives data for 654 women. So that's our sample size right there, 654 women, aged 20 to 29 years. The mean body mass index of these 654 women was X bar equals 26.8. So there's our sample mean. On the basis of this sample, we want to estimate the mean body mass index mu in the population of all 20.6 million women in this age group. All right, so let's go back to our main screen here. So N 654. So example 14.1. So N, the sample size of this sample is 654 women. The sample mean is 26.8, and the book doesn't give the units for that. Body mass index, it's just an index, so actually I don't believe there are any units for that. Okay, so the goal here is to estimate the mean body mass index of all the millions and millions of women in this age group. And then one more thing, back to the example here. It says to match the similar conditions, I'll talk about that a little bit later, we will treat the NHANES sample as a simple random sample from a normal population with a standard deviation of sigma equals 7.5. Now, let's just write that in here. Sigma equals 7.5. Now, of course, in real life, we're not going to know this number. I mean, how do you know the population standard deviation if you don't even know the population mean? And we're trying to estimate the population mean. But for now, we'll just pretend we know this number right here. And in other chapters, we'll deal with how you do these calculations when you don't know this number. But for now, we'll just pretend we know the standard deviation of this population. And also, we're told in this example that the population is normal. The mean, the body mass index of these women forms a normal distribution. All right, so first of all, what does the sampling distribution look like for this? Now, keep in mind, we don't know the mean of the population. That's the whole point of this question, is we're trying to estimate the mean. So in the middle of our sampling distribution, let's write sampling distribution here. So this is all the possible x bars. Okay, so we don't know. I'll just use the symbol mu there. But what we do know is we have information about the standard deviation of this sampling distribution, because if you go up 3 standard deviations, down 3 standard deviations, each standard deviation is sigma over square root of n. So let's go ahead and calculate that right now. So the standard deviation of all possible x bars is equal to sigma over square root of n, and we know these numbers. So sigma is 7.5. N is 654, so square root of 654. Okay, let's do this calculation here. I'll just pull up the computer's calculator here. So this does have a square root button on it. Yeah, square root button right there. So let's do 654. Hit the square root button there. 25.57. So I've got 7.5 divided by 25 point. What was it again? 5734. That's probably good enough. 5734. Okay, so now I got to divide. So I'm going to divide 7.5 divided by 25.5734 equals 0.29327. Probably we could just round this off to, how about 0.293? Okay, now the the standard deviation of the population is pretty big, 7.5. However, because our sample size is so big, we're going to have a very reliable sample result. And so our standard deviation of all the possible x bars is 0.293 because out of a sample size 654, you're almost guaranteed that a few of the women will be above average, few women below average, most women will be close to the population mean, and so altogether, the standard deviation of the x bars, all possible x bars, 0.293. So now we can use the fact that we know because our sampling distribution is normal, because our population is normal, we can make the statement that 95% of the time our x bar will be within two standard deviations of the real population mean, which we don't know, but we're trying to estimate. And so let's take this 0.293. In the textbook, they just round that to 0.3, so I'm going to go ahead and just round it to 0.3 as well here. So it's approximately 0.3. Okay, so in other words, 95% of the time, our x bar, in this case, what was it? 26.8 right there. So 95% of the time, our x bar is within two of these standard deviations. So two standard deviation, one standard deviation is 0.3, two standard deviations of the sampling distribution is 0.6. So 0.6 of the real population mean, whatever that is. So now we can put this all together. Our sample mean was 26.8. So 26.8 plus or minus 0.6, which then gives us, let's see, 26.8 minus 0.6 is 26.2, and then 26.8 plus 0.6 is 27.4. So this 26.8 plus or minus 0.6, it means 26.2 to 27.4. So there's our confidence interval. Now for homework and for tests and so forth, you can actually give your confidence interval in either one of these forms right here. But what does this tell us? It tells us that so we're 95% sure, we're 95% confident. Here's our final conclusion here, that the true population mean, the true population body mass index, so the body mass index mean of the population, is between 26.2 and 27.4. Okay, there's our final conclusion. That is the whole idea of confidence intervals. And so this 0.6 is called a margin of error, right there. Let's write that here. Put an arrow, margin of error. And now, of course, we're only 95% sure. It's possible that this particular x bar, or this 26.8, was just one of those crazy samples. Maybe it was a huge underestimate, and maybe the real population mean is 29 or something, or maybe this 26.8 was an overestimate, was more than two standard deviations greater than the population mean, and maybe the real population mean is 25 or something. But 95% of the time, our x bar is within two standard deviations, so that means if we go plus or minus two standard deviations, we're pretty sure the population mean is between these numbers. And now, later in chapter 14, we'll get more precise, but that's the basic idea for now.